Welcome to Multidisciplinary Design Optimization, last lecture. Today we will conclude and summarize the lecture. So let's get started. And we now jump back to the beginning, where we talked about the definition of optimization. And I would like to repeat this one important sentence. Optimization is finding the best design within the available means. There are three important ingredients in this sentence. One of them is finding, so it's about implementing search algorithms. Another ingredient is best. We need to have a clear understanding of how to assess designs and how you choose the best design among different designs. And the third ingredient is the available means, referring to constraints and requirements. So stressing that a very light design, so optimal with respect to mass, is of no use if it fails. So there are requirements that need to be satisfied, like, for example, with respect to strength or other performance aspects. There are, in structural optimization, three types that we would like to distinguish. There is sizing optimization, where you have where you modify design variables directly, design variables that represent features or properties of your mechanical structure, like the thickness or the cross-sectional area. Then there is shape optimization, where you change the geometry in an indirect way. So you could, for example, change the diameter of a hole or the detail shape related properties of this hole, and typically remeshing in a finite element solution would be required. And then there is a very different kind of optimization that we did not talk about in this lecture, which is topology optimization, where you vary the design with respect to its topology, meaning that you remove or add holes. So our focus was on sizing optimization if you think in terms of structural mechanics. So multidisciplinarity is related to many different disciplines. So sometimes what a discipline is can be ambiguous, but often people would associate disciplines with the kind of analyses they use. So fluid mechanics would be a different discipline from structural mechanics. Sometimes people like to distinguish disciplines by their functions of the product. So acoustic properties versus durability. And characteristic of multidisciplinary optimization is that you have goals that you pursue from different disciplines, and you need to somehow look at them in a comprehensive way. So you cannot only optimize with respect to one discipline. You need to adopt the view that includes all disciplines. And this is a very important aspect of multidisciplinarity, and that makes optimization more complicated. So you do have increased complexity because there's interaction between design variables and those multiple goals, and it's all about seeking the overall best design. And what overall best means is sometimes difficult. And what you can see here would be a illustrative example of what designs different parties or different disciplines would come up with. So a structural designer would probably try to minimize the wing root moment, a engineer that tries to minimize the drag would optimize the aspect ratio of the wing, which make the wing longer and therefore increase the wing root moment. Somebody who is responsible for fuel consumption would try to optimize by the bypass ratio, or somebody who would like to maximize the number of passengers would maximize the fuselage diameter. And these things may be in conflict with each other, and multidisciplinary design optimization is all about finding either a good compromise or resolve these conflicts. The problem statement that is typical and that also can be used as an interface between the engineering design problem and an algorithm looks like this, where we use the vector of design variables, the objective function, equality and inequality constraint functions, and upper and lower bounds for your design space. This diagram here shows the flow of information in a design problem. So a system that with certain properties would be described by system equations. Once you solve them, you would produce system responses, and out of those system responses you would extract the quantities of interest which you would like to either subject to constraints or you would like to optimize. So the dependency that we are after in optimization is between design variables and quantities of interest. So it's not the dependency between spatial coordinates and material properties, for example. Yeah? So it's all about design variables and quantities of interest. And we we showed you this nice little graph that that documents the most important dependencies by distinguishing design variables and quantities of interest, and providing information what needs to be done with those quantities of interest. So either minimized or maximized or subject to an equality or inequality constraint. The two-bar truss was our representative structure that we use to formulate design problems or engineering problems. So the simplest example was this. We like to find the best setting of design variables such that some system performance value would be extreme. So in this case, the displacement was supposed to be minimized. And from there, we could generalize to different categories of problems. So in particular, unconstrained versus constrained problems. So here to give you an example of an unconstrained problem, the one that we first encountered by looking at the two-bar truss problem. And once we bounded that unconstrained problem appropriately, we would make it look a little nicer. Bounding in this case would mean that you bound your design space in order to look at the relevant part of the design space that you want to analyze for your design purposes. And by looking at this, we can start classifying functions, objective functions, constraint functions, and also problems. This would be a convex objective function as opposed to a non-convex objective function. And with convexity, there are some nice properties associated. So once you have an optimum for a convex function, you know you found the global optimum and you can stop iterating. So this is also a non-monotonic and non-linear function. So monotonic and a linear function that is automatically also monotonic would look like this. And here you can see, well, you can see it in the handouts, would be a function that is nonlinear but monotonic. Then we also distinguish between continuous and discrete problems, and in this lecture we only treated continuous problems. In particular, we looked at algorithms that can analyze problems that for which we did not have closed form solutions, but that we could look at as black box functions, and the system responses of which would be produced by numerical methods like finite elements. In addition to the constraint problems, there is the, well, more general class of constraint problems. And when I say more relevant, in reality, you would almost always, for a problem of practical relevance, encounter an optimization problem with constraints. So treatment of constraints is absolutely essential, and therefore we also focused a lot on constraints in this class. In optimization, it is very important that you understand your problem, although in particular in high dimensions, it may be not very intuitive. And we distinguish between formula analysis and sampling that you can use to analyze your problem. And attached to each of these approaches are different analysis methods. So when you look at a formula, you just by looking at it could get an understanding of what the problem looks like. However, of course, often you do not have these formula available. And therefore, we also need techniques that would work without formula. So this method, or the most important method, would be sampling. And then, of course, you can't look at the structure directly, but you could look at other things. You can look at plots. And therefore, you would, for example, get an idea that apparently you have a monotonous input-output relationship. So you could also derive sensitivity measures from plots. So by looking at gradients, for example. When you sample your input space, so shown here would be an example of a random sample that you would use for Monte Carlo methods, or a full factorial sample. Then you can use other techniques, so like projection of sample points that we discussed, or statistical measures like correlation coefficients, or surrogate models like the regression model that we also discussed. From the regression, from the surrogate models, you can, from the regression model, you can derive an average slope that is a sensitivity measure, and with the correlation coefficient and the gradients, we have three sensitivity measures that we discussed in this class. Before you think about optimization algorithms, you need to specify the target or the optimal design mathematically. So you need to specify optimality conditions. And the necessary optimality conditions for both constrained and unconstrained problems with equality and with inequality constraints are the Karouche-Kuhn-Tucker conditions. They consist of the first order gradient of the Lagrangian being 0, the equality constraints and the inequality constraints themselves, and the so-called complementary slackness condition, which serves like a switch where either the Lagrange multiplier of inequality constraints is 0 or the constraint function is 0, and the condition that the Lagrange multiplier must be positive or 0. Okay, and there is a nice geometrical interpretation of this. So if you think of a design problem with two design variables and two inequality constraints, the downhill direction would be this. So this would be the negative gradient, therefore the gradient of f would point in this direction. Then the gradient of the constraint function, of the first constraint function, would point in this direction, and the gradient of the other constraint function would point in this direction. And for this to be optimal, the gradient of f needs to be a linear combination of the two gradients of the two constraint functions. And well, this is optimal if the Lagrange multipliers mu1 and mu2 are both positive. If one of them were negative, then this would be not the uphill direction, and therefore it would not be optimal. There is a nice physical interpretation of Lagrange multipliers. So in this simple example, we showed how a Lagrange multiplier would evaluate as the force that makes sure that the constraint, here in this case, that the vertical position is fixed, is satisfied. The general optimization problem is now written in a vectorial way like this. And there is a nice analogy between optimization on a finite dimensional design space and optimization on an infinite dimensional design space. So where your design variables are a function and not a finite dimensional vector. And this analogy leads us to the calculus of variations. And with a generalized definition of a gradient, you can translate the optimality condition for finite dimensional optimization problems to infinite dimensional optimization problems. And using this, we computed the optimal cross-sectional area of a cantilever beam. Then finally, we started talking about optimization algorithms. So there are many ways to categorize them. One way that we presented is that we categorize them by 0th order, 1st order, and 2nd order, referring to the order of differentiation, and by unconstrained and constrained problems. So the typical 1st order gradient optimization problems would be these: the steepest descent algorithm, where you just progress or advance in the direction of the gradient. Then the conjugate gradient method, where during your iteration you add some kind of inertia or viscosity to your search direction. Then the modified Newton's method, where you actually use 2nd order information so the 2nd order derivative of your objective function, where you compute the Hessian with the disadvantage that it's actually quite expensive. And a 1st order method, which is called quasi-Newton method, where you approximate the Hessian by an update using gradients. So this is a very powerful technique because you do not need to perform the 2nd order derivation, but you have a similar quality of the results. And these methods provided the search direction of your increment, and in that search direction you would perform an inexact line search. And for that line search there are three techniques that are relevant. The first one is called bracketing, that provides you an interval that includes an optimum. Then there is sectioning that helps you to narrow down that interval. And then finally, on that resulting interval that you would get from sectioning, you can still improve your estimate of the actual location of the optimum by an approximation technique, which is essentially the fit of a quadratic function. And that would tell you on this line, on that search direction, where your best candidate is located. Okay. So a very important technique to treat unconstrained problems is that you turn them into, a very important technique to treat constrained problems is that you turn them into unconstrained problems. And you can do that either by barrier functions or penalty functions. Barrier functions block the way to the infeasible region by letting the penalty term approach infinity, whereas penalty functions do not block the way entirely. And the advantage of the penalty function is that you could use it for equality constraints. But the disadvantage would be that you may end up in the infeasible region and may have to correct your optimization result after convergence. And barrier and penalty functions are such that you employ a coefficient r, and by letting r go to 0, you would reduce the effect of your barrier function on the error that you make by using barrier or penalty terms. And you can tell how by making r smaller and smaller, your optimum would converge to the real optimum. So in the second lecture on algorithms, we discussed evolutionary algorithms and the important algorithms SLP and SQP. SLP is short for sequential linear programming, where you solve possibly nonlinear optimization problems by a sequence of linear optimization problems. So if you look at these nonlinear constraint function here, for example, you would approximate this by these lines, and you would always linearize around a reference point from which you look at your problem, and then would come up with an intermediate optimum that is here. And then you linearize again and you go on. So this is a fairly fast approach, but sometimes has limited convergence properties. And sequential quadratic programming is therefore often preferred, where you solve nonlinear optimization problems by a sequence of quadratic optimization problems. An important keyword for SQP is the active set strategy, where you turn off and on constraints such that you can, for each iteration step, you can look at your problem as a quadratic optimization problem with equality constraints. The differential evolution algorithm is an example of evolutionary algorithms. And well, in some sense, they are less structured, or they don't rely on gradient information as the other algorithms that we discussed. And they're typically used for global optimization problems, where you cannot rely on neighborhood information as well as you could do for problems for which you apply SQP or SLP. And the basic operation steps that you would employ are the recombination of your candidate designs, the mutation of them, the evaluation, and the selection. If you have many objectives in your design problem, then there are 3 techniques to treat the fact that you have to decide how what objective you give preference. So if you have a couple of objective functions, you may get into a position where you need to either improve F1 or F2, and there are 3 techniques to deal with this. So the Pareto optimization technique says, I'm not going to compute one optimal design, I'm just computing all the designs that are not dominated. So not dominated designs would be those where there exists no other design that is better with respect to all other quantities of interest. The second technique relies on specifying an objective function that essentially collects all quantities of interest and boils it down to one scalar value. And in this definition, you embed preference of the designer. And one way to visualize this is by looking at this graph here. So the contour lines of your objective meta function, as we called it, would be here given as these thin lines. And the possible system outputs, so the possible combinations of quantities of interest, would be on this thick blue line here. And where they run tangentially, so the contour lines of your objective meta function and your Pareto front that separates the region of realizable designs and the designs that you cannot realize, at this tangent point you will get your optimum. And there is no general rule how you should construct or design your objective meta function. There are only, let's say, 3 basic ways to do it. There are other ways to do it, but the linear, the quadratic, and the worst case type, they are useful for particular purposes. What kind of preference they introduce to the problem you can see by looking at these plots, where you compare the contour lines of your objective meta function and the regions of possible system outputs. We also looked at these 3 types of objective meta functions for different design problems. Here we distinguished between less is better and nominal is better design. And another class of design problems where you do not try to well, which is different from classical optimization. Here you just try to find a design that satisfies your requirements and then possibly improve it further. So for this class of design problems, we also constructed objective meta functions. And the ones you see in white here are those that work in general. So in particular, the worst case type is good for the treatment of requirements. And the linear objective meta function would be the one that typically works for the X is better type design. Then we introduced a different kind of optimization, the so-called solution space optimization. And the motivation for this was that optimization results are often not robust or not reliable. In this particular case, the result would be neither. So upon a small variation of your design variables, the design would actually fail catastrophically. So what you want is a design that is away from that failure region. And the problem with classical approaches like reliability or robustness analysis is that you would have to specify how far you want to be away. And this how far you want to be away is associated with a knowledge of existing uncertainty. And you typically don't have that. You just don't know how uncertain you are. So therefore, a different optimization problem is introduced where you say, well, we just want to be in a region that is as large as possible. So this is like, in some sense, this is saying we want to be as far away from the failure region as possible, but instead of maximizing the distance to the failure region, what we do is we look for rectangular regions of good designs, and the reason for that is that we can use those edges of the rectangles as intervals for target regions of systems design. So the new design problem that is to be solved here is find a box specified by upper and lower limits such that within that box all designs are good. Mathematicians also call that an inscription problem. So this is an optimization problem motivated by robustness and the fact that we don't know how uncertain we are. We just want to be in a region that is as large as possible and has this simple rectangular structure. And then we introduced 3 techniques how you can solve solution space optimization problems. One of them was the stochastic iteration technique, where you produce a candidate box. You sample within this candidate box, remove the bad sample points, and then extend it. And this way it will grow into the good design space. After the so-called exploration phase, you would just remove bad design space a couple of times until you're pretty sure that you only have good designs included. And then you have a box that is close to the optimal box. A non-stochastic, that is a deterministic way to approach this is the so-called corner tracking technique, where you essentially connect requirements or constraints with one corner of the box and come up with an optimization problem that where the design variables are the location of those critical corners, and this way you can use classical optimization techniques to solve this problem. And then finally, there was a manual technique that you can use to construct solution spaces, and we call this the selective design space projection, where you work on two-dimensional diagrams that are the projections of higher dimensional slabs of your design space, and that help you to identify this high dimensional a box of good designs. In the previous lecture, we then discussed systems design and the reasons why it is particularly difficult. So we identified 4 complexity drivers that add to complexity. One of them is that often your interaction between design variables is very non-intuitive, that you have different parties involved that work on the same design problem, and they produce information in a sometimes possibly chaotic way, and you need to orchestrate this. Then you have many design goals in complex systems design, and on top of that you may even have another level of complexity, that is when you intend to build products, or in this case vehicles, by reusing components that you use also in other products. So these complexity drivers can be modeled as something that you can call epistemic uncertainty. And this epistemic uncertainty leads to a chicken or egg problem. So in an early design phase of a complex system, you have different design parties possibly waiting for each other to make the first step, that they can then make the next to push the design in the optimal direction from their perspective. But of course they're all waiting with respect to each other, therefore you have a chicken or egg problem. So one way to treat this is essentially a design approach that is built on solution space optimization, where you model your product as a hierarchy of variables, design variables, and quantities of interest, and intermediary variables. And depending on your design perspective, for example, if you assume this focus here, then the top variables would be your design variables, and the lower levels variables would be, the top variables would be your quantities of interest, and the lower level variables would be your design variables. Or if you assume this focus, you would have your design variables here, and here your quantities of interest. And you document all of these dependencies in a dependency graph. Then you establish your quantitative relationships in a bottom-up sense. So this is typically your finite element simulation or your computational fluid dynamics simulation, where you compute aggregated quantities or system outputs from detailed design variables. And then you invert the direction by specifying target regions for your output, and from that you compute target regions for your input. And this is what you can do with solution space optimization. So this is the evolution of our lecture. So we started out very simple. Then we added quantities of interest. We added many design variables. Then we added goals. Then we changed the perspective from optimization of one design to the optimization of solution spaces. And then we talked about how this can be seen as a part of a bigger thing, and how this actually can be decomposed again back into smaller optimization problems.